Hello, my name is John Hoagland, and I'm going to be presenting an environmental trifecta, coupling desalination with carbon mineralization to eliminate carbon dioxide and brine disposal, store energy, and reduce salination of groundwater. There's a lot to that title, I know. First, a little bit about myself, my background. My degrees are in geology. I have worked in government, academics, as well as the private sector, and taught environmental geology, glacial geology, climate geology, and groundwater modeling. I currently have my own consulting firm and founded the nonprofit Carbon Negative Water and Energy to pursue these carbon sequestration projects. Looking at the title a little bit closer, coupling desalination. First, what is that? Desalination is basically the removal of salt from brine, which can include seawater. Brines are very salty solutions, including seawater. Technically 35,000 part per million salt in seawater. And as freshwater sources get stressed around the world, we're looking to use desalination methods to remove salt from the oceans or from other sources of brine to produce fresh water. That takes energy to do that. And so as an energy consumer, then that process produces greenhouse gases, carbon dioxide from the use of energy. But the salt from the desalination process can also be used to lock up that carbon, carbon mineralization, and I'll discuss that in some detail. So we can eliminate the CO2 in that process. It's called carbon sequestration, when you lock up the CO2 before it enters the atmosphere. And we can also eliminate the brine disposal because we're using the salt to lock up the CO2. The process produces hydrogen, which can store energy. That's the second part of the trifecta. And the reduction of salination of groundwater is something that I recently discovered when I gave a variation of this talk to the National Groundwater Association. The speaker after me was talking about the buildup of chloride levels in groundwater because of the use of road salt. And one of the byproducts that I have here is an alternative to road salt that could reduce the buildup of chloride in groundwater. So there's a lot of benefit that could come from this, and we'll move on to the first slide. I mentioned that desalination requires energy. This chart is from a desalination engineering textbook, and it shows different methods of desalination. The different methods are not that important at this point. The one on the left, the multi-stage flash, MSF, is the kind of desalination that most of us think of, distillation, where you use heat to boil water off of the salt, leaving the salt behind, and then recondense the water. And that's a very highly energetic process. It takes 17 kilowatt hours to produce a cubic meter of fresh water using that method. And the other method that's probably deployed more commonly in the United States and is the SWRO, salt seawater reverse osmosis. Reverse osmosis methods require less energy, 4 kilowatt hour to produce a meter cubed of water, but that energy is mechanical energy, so it's a little bit more expensive to make that form of energy. It has to be converted from a fuel source, usually by driving electric powered pumps. So you have to generate electricity, and there's always some losses involved in doing that. Believe it or not, the multi-stage flash method on the left with 17 kilowatt hour, even though it requires more energy than the other processes, it's the most used worldwide because all you need is heat, and you can produce heat pretty easily, especially in the Middle East. So multi-stage flash is used for distillation. But if you're going to do reverse osmosis and drive electric engines, you're going to be burning a fuel, and that can produce the CO2. So 4 kilowatt hours is a good number to think of in desalination in the United States and perhaps the rest of the Western world, where reverse osmosis and engines are used to drive the desalination process. So move on. So I hope to cover in this talk a couple of items. The solutes, which are the salts basically that are in the seawater, the solutes that are left over from the desalination, we call that concentrate. I think of orange juice when I think of concentrate, but this is the leftover salt after you extract the fresh water from seawater. Those salts are used as a substrate to capture the carbon dioxide. Sulfur and nitrous oxides as well, nitrogen oxides, sulfur oxides, SOx and NOx, which are gases that lead to acid precipitation. So there are several scrubber technologies that remove SOx and NOx from the flue stack of power plants to clean up with respects to acid precipitation. This process that captures carbon dioxide also can serve as a scrubber technology to remove SOx and NOx. Brine discharge is eliminated because instead we're going to use the salt. The brine and water resources are going to produce commodities. The minerals, the salts that we mine from the solution, are going to be used to lock up carbon dioxide. And one of these can be used as a de-icing agent. And this is the key that a recent discovery, if you will, that I added to this list by having talked to the National Groundwater Association. It pays to go to scientific conferences. Anyway, the other commodities that we produce are gaseous, including hydrogen, which can be used for energy storage. The freshwater production is increased from most desalination processes because we're using the extra salts that are normally left over in the concentrate. We get that the salts, even at that high concentration, are small in comparison to the water. So as you use up the salts in the other part of the solution that's left over, you increase the water take. The remaining solvent left over from the solute extraction is one source of the increased freshwater production. We also can stack capture the water from the combustion of the hydrocarbon fuel. So when you burn gasoline or natural gas or coal, you produce CO2 and water. You can capture that water if you're stack capturing the rest of the stack. And you can then also produce water whenever you use the hydrogen. You can either burn the hydrogen, call that combustion when you react it with oxygen gas, and produce water, or you can do electrolytic oxidation of the hydrogen in a fuel cell. Either way, the output of that process is water.